Good afternoon, ladies and gentlemen. So I would like to present the work of mine and my colleagues, Mr. Jarmil, Vlach and Růžek. We are affiliated with Czech Aerospace Research Center, located in Prague, in Czech Republic. So the work will be about the compressive test of the 5-stringer panel made from thermoplastic polymer. So at the beginning, I will show you some test results. It's a motivation for the work, but the aim of the presentation will be the finite element analysis of the compression test. We will be interested in buckling behavior and strength behavior. So the panel was made from thermoplastic composite polyether keton reinforced by unidirectional carbon fibers. The material properties are shown on the left side that are useful then in the finite element analysis. The panel was composed of several subparts. It was the flat skin and 5 webs. Each web consists from the stringer and from the cap. All these parts were joined together by the filler. At the end of the panels were applied the aluminum blocks in order to apply regular boundary conditions. We have tested 2 panels. It was the Pristine panel without no crack and the cracked panel that included the delamination between the center stringer and the skin in the center part of the length of 70 millimeters. At the beginning of the test, it's good to make some hand calculations. So in order to know how the panel can behave during the test, I assumed the failure strain of 0.015 regarding to strengths of unidirectional specimens. If we will assume that all layers and all parts of the panel will carry the load, we can get the load of 1 meganewtons, but it's not true because we are expecting buckling. Searching literature, we can find some diagrams regarding the buckling of plates. For our case, with the constrained ends and supported sides, we can expect it 4 or 5 half wavelengths as a buckling, and the appropriate buckling load will be about, we can expect it at 120 kilonewtons. But it's so, sorry, if the buckling will appear, we need to consider that not all the parts of the panel will carry the load. So the buckling cause the deformation of the skin, and then the skin will not contribute to the load transfer, so the webs and caps will be the main loading path. Then we can expect the strength at about 370 kilonewtons. But it's still not so true because there is some effective skin under the stringers, and then we can obtain about 500 kilonewtons as a strength. We have chosen the appropriate test machine in our laboratories with the capacity of 1 meganewton. The panel was implemented in the center and loaded by the block with the supports, anti-buckling supports. We had also data acquisition system consisting of strain gauges, LVDT sensors, and Aramis DIC system. We also applied standard cameras and high-speed camera for the point of the rupture of the panel. From the point of the analysis, I am mostly interested in the load displacement curve. This is the data from DIC acquisition system, and I can say that for Pristine panel, the collapse of the panel occurred at 476 kilonewtons, and for crack panel, a little lower. Interesting is the point before reaching 200 kilonewtons, there is seen the change of the stiffness since there was the buckling. Now I will show you the records from fast high-speed camera. The clip length was of 17 milliseconds with the 25,000 frames per second. This is the Pristine panel. the collapse initiates in the center part, and you can see that at the end we have total destruction of the panel with delamination of the cap, web, and the stringers from the skin. There is also a lot of debris flying around the hall. For the cracked panel, the situation is very similar. We also expected that the damage will be initiated in the center where the delamination was located. There is also the disassembling of the separate parts, and in this case there are also seen very big debris flying from the panel. It can be dangerous since anybody can be hit by this debris, and some data acquisition system can be damaged. It also happened in our case. Looking in more detail, it's seen that the damage for Pristine panel was initiated in the center. Then appeared the crack in the cap, and the failure was across all panel. It occurred in 2 milliseconds. The cracked panel was similar, but at the beginning we had distortion of the center panel due to the delamination. Then again the disassembling, the disbonding of the cap from the web occurred with continuing damage through all the panels. So the aim of the work was to simulate this test via finite elements. Everybody who have access to commercial finite element software like ANSYS, Abacus, probably he will build a very simple model like I did. It's a shell element model with skin, web, and cap. These subparts are connected by tiding. In the case of the cracked panel, there was omitting the tiding in the center. I used Abacus software. The first analysis is the buckling analysis. We will obtain a lot of eigenmodes with very close eigenvalues. We cannot expect these eigenmodes during the test. But what is interesting is looking for the difference of Pristine and cracked panel. It's the local buckling in the center part where the initial delamination was present, and it's at the load of 290, 380, and 470 kilonewtons. So we can expect some local buckling in the delaminated area. The second analysis, the further analysis, is the implicit analysis that we can perform. At the background in this graph is shown the DIC data from the test, and we can see that the match of the analysis is relatively good. Also, the change of the stiffness before the reaching 200 kilonewtons. But the implicit analysis was not finished. During the simulation, there was no collapse of the panel because of numerical difficulties at the end. It's connected to hashing failure criteria. For example, this is showing the matrix tension criteria. For the Pristine panel, the maximum values were under the webs in the locations of the half waves that appeared during the buckling, and for the cracked panel, it was at the crack fronts. In order to get beyond the point of the numerical instability, we used explicit analysis of this simple model, and for Pristine panel we get above the value that was reached during the test, above 1500 kilonewtons. There were also development of buckling modes, 3 half waves in one section till to 4 waves. The collapse of this panel during this analysis using simple model was due to the failure of the stringer. The cracked model was a little different because we had a local buckling at the load of 300 about 30, it's the local buckling in the area of initial delamination, where after this local buckling and some local failure of the skin, the panel was still able to carry the load up to the 400 kilonewtons, and then the collapse of this panel also appeared. Plotting the damage in 5 criteria, fiber in compression, we can see that for Pristine panel, it was the failure across the whole panel, but for the cracked panel, it really occurred at first in the center part in the skin, and then it also spread across the panel in U shape. In order to, as I show you the record from the test failure of the panel, we would like to also have this behavior in our model and to cover the delamination process. So we moved to build the detailed ply-by-ply model. It means that every lamina of the composite was represented by layers of element. There was also filler included, and the connection of these parts was made by cohesive elements. This is the cap and the web, and the web and the skin detail. So the cohesive elements included cohesive zone modeling. The crack was realized by emitting the cohesive elements. Here are the results of Pristine panel. The initial part of the low displacement curve is very similar with simple model and with test data, and after reaching 200 kilonewtons, we have little oscillations of the solution. It's due to the mass scaling applied during the analysis. But at the end, you can see that we obtained really the disassembling of the panel to separate part, to subparts. The crack panel was similar, but we obtained the local buckling in the center part where the initial delamination was located, and the displacement of the center skin also occurred with subsequent failure and the damage. We obtained lower maximum load. We can also plot the status of cohesive elements. This is the back view with the hidden skin. So these lines represent stringers, and we are going from back because, as I said, back skin. So for the Pristine panel, the delamination occurred at the second stringer, and from the cracked panel, it was at the crack front of the delamination from this one side and then also from the other side. At the end, we have this body all stringers. So this is explicit analysis of Pristine panel. At the beginning, we have smooth low displacement curve, and then when the buckling occurred, some oscillation appears. At the end, you can see also this assembling of the two subparts. Very similar for the cracked panel. From the tested data acquisition system, we can know the load when the buckling occurred, the 3 half-ways and 4 half-ways for Pristine and cracked panel. Similarly, we can compare the finite element analysis results with the first buckling load and also the second buckling load. The first are occurring of the 3 half-ways and the second of 4 half-ways. The simple model works very fine. The explicit model is not so good, but it's, as I said, due to applied mass scaling. The failure load is best for the catching. The failure load is best for the explicit ply-by-ply model, since we catch the real damage mode of the panel. It was the delamination that initiated the collapse of the panel. So let me conclude. This work we have tested Pristine panel and cracked panel, and we applied 2 basic models. It was the simple finite element model and the detailed ply-by-ply model. And also at the beginning we did some analytical solution. 2 models has also advantages and disadvantages. Simple finite element model, easy to build, good buckling prediction, but it's not unable to cover the right failure mechanism. The detailed ply-by-ply model has a lot of difficulties, but we can really model, we can really model the failure mode is the domination. So, thank you for your attention, and I should note that the work was supported by Teotest, the European project. Thank you.
Thank you for your presentation. Any questions? Yes.
What was the reason for this design to attach the cap on the web? I mean, it's a thermoplastic material. You can just bend that, and then because what I've seen is that it's exactly there where it feels actually.
It's due to the manufacturing process. It's the new method how to manufacture these panels. It's the consolidation of all parts at once. So the manufacturer is able to manufacture the whole section of the stringers and webs.
But why not taking the web and bend it?
Maybe it will be the same option.
I've never seen such a design and it fails.
The basic is that they will prepare flat panels, they cut them, and then they will assemble a whole panel. It was seen that the lamination in this connection is the critical point. Yes.
Because you have also because it's asymmetric also. Yeah? If I would design like something like that, I would at least make a T-stringer, then it's symmetric. Because if you now you have an offset and it tends to bend.
If there will be applied some reinforcements in these sections, the results will be better. Maybe. This is one of the attempts how to build such section.
Thank you.
Thank you.
More questions? Yeah, in fact, this was my question. Okay, thank you.
Thank you.